Prepare to be captivated by the dual enchantment of Bezout's identity as we unravel its mysteries in this illuminating video. In our mathematical adventure, we'll not only delve into the profound significance of Bezout's identity in the realm of Diophantine equations, but also explore its intricate relationship with the fascinating world of continued fractions. Join me as I decipher the power of Bezout's identity in solving Diophantine equations, those perplexing puzzles that require integer solutions. With clear explanations and engaging examples, I will show you how this identity serves as a guiding light, enabling you to unlock the integral solutions hidden within seemingly inscrutable equations. But our journey doesn't stop there. Brace yourself for a revelation as we unveil the remarkable connection between Bezout's identity, Diophantine equations, and continued fractions. Witness firsthand how this mathematical marvel interlaces with the art of expressing real numbers through never-ending sequences of fractions, leading to astonishing approximations and insights. Whether you're a mathematics enthusiast, a curious learner, or an avid explorer of the hidden ties within numbers, this video promises to elevate your understanding of both Diophantine equations and continued fractions. Join me in deciphering the intertwined elegance of mathematical concepts that have perplexed and delighted minds throughout history. My fellow math adventurers, uh, as you can tell from the introduction, today we're going to be talking about Diophantine equations, how to solve them using Bezout's identity, and how all of that can be encapsulated into continued fractions, right? So what is a Diophantine equation, right? Diophantine equations are any in which there are more variables than equations. For instance, as you can see on the screen, one singular Diophantine equation can be given as ax plus by equals c, with the the variables being x and y. So there's two variables and there's one equation, which means that's a Diophantine equation. Okay. How do you go about solving? How do you find out what two values for x and y can solve a Diophantine equation? So I have an example on the screen, right? What would be the solution to 533x plus 195y equals 0? What two integers, x and y, can multiply to 533 and 195 where the solution is 0? Well, that's pretty tough if you don't know what you're doing, if you don't have if Euclid wasn't around, right? We didn't have Euclid um with his algorithm, right? The Euclidean algorithm. This is a way to use the Euclidean algorithm to solve Diophantine equations using Bezout's identity, which is this table that you see on the screen, and how all of that can be related to continued fractions if you want. Okay, so let's just see what this is about. How do we even do this? Well, we set up the table of the two uh, integers that are already in the Diophantine equation, 533 and 195 here on the left. In the middle, we put 1, 0, 0, 1. More on that later. And then this whole thing here are going to be the quotients when you divide. Okay, so this is how you do it. These are the steps. First, how many times does 533 go into 195? Right? That would be 2. And what's the remainder? So 195 times 2, 533 minus that gets you 143. The remainder is 143. So 533 divided by 195 is 2, remainder 143. Okay, now this is where the 1, 0, and 0, 1 come into play. You want to multiply your quotient with the bottom row, okay, and then subtract the top row from the bottom, right? So for instance, 2 times 0 is 0, 1 minus 0 is 1. 2 times 1 is 2, 0 minus 2 is negative 2. Okay, let's continue. Now we just keep going up the table. We do the exact same thing. So now we say how many times, what's 195 divided by 143, right? Well, 143 could go into 195 once with a remainder of 52. Okay, now we do the exact same thing. We multiply 1 to the bottom row and then subtract the top row then subtract it from the top row, right? So 1 times 1 is 1. 0 minus 1 is negative 1. 1 times negative 2 is negative 2. And 1 minus negative 2 is 3. Okay, now we go to the next one. What's 143 divided by 52? 2 with a remainder of 39. Okay, so now we do the same thing. 2 times negative 1 is negative 2, and 1 minus negative 2 is 3. And 2 times 3, which is 6, and negative 2 minus 6 is negative 8. Right, not too bad. Now, how many times does 39 go into 52? Once, with a remainder of 13. And we do this again. 1 times 3 is 3. Negative 1 minus 3 is negative 4. And 3 minus negative 8 is 11. Okay, now how many times does 13 go into 39? 3. No remainder. And we do our last column fill in here. 3 times negative 4 is negative 12. 3 minus negative 12 is 15. And negative 8 minus 33 is negative 41. And since we're at 0, we are done. We have finished Bezout's identity. We can now solve this equation. How? By looking at the last row right here. Okay? This is telling us that 533 times 15 plus 195 times negative 41 is going to equal 0. Right? So 533 times 15 plus 195 minus 41 equals 0. And this is true because we did this 100% correctly. So this is one example of it. It could be, as long as the two initial numbers have a GCD of 1, then we're good to go. These numbers can't be like 2 and 4, for instance, right? Okay, now what's really cool is you could use the quotients of Bezout's identity to get a continued fraction that is equal to your initial two numbers divided by each other. So, for instance, 533 divided by 195 is going to be equal to the continued fraction 2 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 3. Okay, I know that was a little fast, but I'll show you. There's your solution again, and there's your continued fraction. This is what this means. So 533 divided by 195 is equal to, and here are your quotients, 2 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 3. And this is just a neat little math mathematical concept that you could use in your everyday life if you feel like it. I'm trying to get the continued fraction out there so you can see the quotients of the same. 2, 1, 2, 1, 3, 2, 1, 2, 1, 3. Okay, here, let's try another one. Let's do another one. I've looked all over the internet, couldn't find anybody or any website talking about Bezout's identity, the Euclidean algorithm, Diophantine equations, and continued fractions. So I thought I'd make a little video of it on my own. So here, take a look at the screen. Let's just, we'll make it a little bit more advanced. Instead of saying equal to 0, we'll have it equal to some number, right? So let's just do a little quick one. Let's say, I don't know, 12x plus 7y equals 3. Okay, just real simple. Set up our table 12, 7, 1, 0, 0, 1. And then the quotients are always on the right side. 7 goes into 12 once, right, with 5 left over. This will be 1, right? 1 times 0, 0, and this will be negative 1. Okay? 5 goes into 7 once, 2 left over, right? This will be negative 1, 1 times 1 minus, and this will be, no, I'm sorry. Negative 1 times 1 is 1, 1 minus, this will be 2. Okay? 2 goes into 5 twice, right? With 1 left over. Negative 2, 1 minus negative 2 is 3. 4, negative 1 minus 4 is negative 5. Okay, and then, let me just extend this. 1 goes into 2 twice, 0 left over. All right, negative 1 minus 6 is negative 7. 2 minus 10, 2 minus negative 10 is 12. Okay, so what have we here? This is saying that 12 times negative 7 plus 7 times 12 is equal to 0. That actually makes total sense, right? 12, negative 7, 7, negative 7, 12. However, we don't want 0. We want 3. So how are we supposed to do this? Well, let's look at this row right here. Okay? Now, this is saying 12 times 3 plus 7 times negative 5 is equal to 1. Okay? So here, let's scroll down a little bit. So this is saying 12 times 3 plus 7 times negative 5 equals 1. So how can we get this equal to 3? Well, let's just multiply both sides by 3, right? Multiply everything by 3, right? And now we get, let's see, we're going to get 12 times 9 plus, right, 3 times 3, plus 7 times negative 15 is equal to 3. And that's all you have to do. It could be 3, it could be 4, it could be 6, it could be 9, whatever. Just multiply everything by that number, and there you go. And what's really cool is that you could do, we have the all the quotients here, so we could say 12 divided by 7 is equal to 1 plus 1 over 1 plus 1 over 2 plus 1 over 2. And there you have it. Right? So this is how you could solve any Diophantine equation, and also solve for any division continued fractions. So that means, so this is saying 12 divided by 7 is equal to 1 plus 1 over 1 plus 1 over 2 plus 1 over 2. Isn't that wonderful? Isn't that great? So yeah, so if you ever are curious and want to solve some Diophantine equations, named after, of course, the great ancient mathematician Diophantus, then by all means, set up a table, solve some, create some quotients, and see what crazy continued fractions you could come up with, right, as you do this. You could get huge, long tables. So, yeah, I hope you enjoyed this brief uh, um, adventure into Bezout, Diophantus, and continued fractions. All right, and until next time, math adventurers, may your journey be filled with mathematical delight. All right, until the next video. Oh, and also, I'm sorry. Don't forget to like and subscribe if you enjoy what you see, because I will be posting more videos like this in the future. Okay, so thank you guys. Bye.